There is a problem at the heart of modern cosmology, and the worst part is this. It is not a small problem, it is not a technical glitch, and it is not going away. For nearly a century, scientists have known that the universe is expanding. Galaxies are moving away from one another, space itself is stretching, and everything we see on the largest scales is shaped by that expansion. That part is settled. What is not settled is something that sounds much simpler. How fast is the universe expanding? You would think that by now, with all of our telescopes, satellites, supercomputers, and decades of precision measurements, humanity would have one clear answer. But we do not. Instead, we have two, and both of them appear to be correct. That is where this story begins. Because when scientists measure the expansion rate of the universe by looking at the early universe, at the ancient light left behind shortly after the Big Bang, they get one answer. But when they measure that same expansion rate using the nearby universe, using stars and galaxies we can observe much more directly, they get a different answer. Not slightly different, not close enough to shrug off. Different in a way that should not happen if our current understanding of the universe is complete. One method says the universe is expanding at about 67 kilometers per second per megaparsec. The other says it is closer to 73 kilometers per second per megaparsec. That gap may sound small. It is not. In cosmology, a disagreement like that is enormous. It means one of the most important numbers in physics refuses to stay consistent, depending on how you look at it. And if that number changes depending on the method, then something deeper may be wrong. Not wrong with a telescope. Not wrong with one research team. Wrong with the model itself. That is what makes this so unsettling, because this is not just a disagreement over a measurement. It is a disagreement over the structure of reality. For years, scientists hoped this would disappear. They thought maybe one of the instruments had a calibration issue. Maybe one of the methods contained a hidden bias. Maybe the data sets were still too limited. Maybe with enough time, better observations would pull the two answers together, but the opposite happened. The measurements improved, the error bars shrank, and the disagreement stayed. Then it got worse. The James Webb Space Telescope entered the story. So did the Atacama Cosmology Telescope. And instead of rescuing the standard picture of the universe, they helped trap it. Because each new instrument kept confirming the side it was testing, the nearby universe still pointed high, the early universe still pointed low. Two answers, one universe. And no accepted explanation that can make both true at the same time. That is the crisis. And tonight, we are going to walk all the way through it. We are going to follow the evidence from the first measurements to the newest data, from the earliest light in the cosmos to the giant galaxies around us now. We will look at what the James Webb Space Telescope found, what DESI found, why dark energy may not be acting the way we thought, and why more and more physicists are starting to suspect that the standard model of cosmology, one of the most successful frameworks in modern science, may be incomplete. Because once you understand what this conflict really means, the universe stops feeling merely large. It starts feeling unstable. And before we go further, if you enjoy deep space mysteries, unresolved physics, and the strangest ideas modern science is wrestling with right now, take a second to subscribe to the channel. We make long-form stories like this for people who want more than headlines. So if that sounds like you, subscribe, settle in, And let's keep going. The number that should not split in two. To understand why this matters, we need to talk about the number at the center of the problem. The Hubble constant. This is the number that tells us how fast the universe is expanding. More specifically, it tells us how quickly galaxies appear to move away from each other as space itself stretches between them. And this is important because the Hubble constant is not just another number in a textbook. It helps determine the age of the universe, the scale of the cosmos, the size of distant structures, and the long-term fate of everything that exists. If that number is wrong, then every larger conclusion built on top of it becomes questionable too. So this is not a minor disagreement. This is one of those foundational cracks that can spread into everything else. Now, the reason scientists ended up with two different values is because there are two very different ways to measure the expansion rate of the universe. The first is by studying the early universe. This method looks at the cosmic microwave background, the faint leftover radiation from a time when the universe was only about 380,000 years old. That ancient light acts like a snapshot of the young cosmos. By measuring tiny fluctuations in it, cosmologists can calculate what the universe was like back then, and then use the standard model of cosmology to predict how fast the universe should be expanding today. When they do that, the answer comes out to about 67. The second method uses the late universe, meaning stars, supernovae, and galaxies much closer to us in cosmic time. This approach builds what astronomers call a cosmic distance ladder. First, they measure nearby stars whose distances can be determined directly. Then they use those stars to calibrate more distant stars called Cepheid variables. Then they use those to calibrate type Ia supernovae, which can be seen much farther away. By stacking these measurements carefully, rung by rung, astronomers can estimate the current expansion rate of the universe much more directly. And when they do that, the answer comes out to about 73. That is the split. Early universe, 67, late universe, 73. Both are supported by years of work. Both come from serious science. And both have been refined again and again. If one of them were sloppy, this would be easy. But they are not sloppy. That is exactly why this became one of the biggest cosmological problems of the last 15 years. Why this is so disturbing. The easiest way to think about it is like this. Imagine two perfectly built clocks. Each has been checked, tested, calibrated, and confirmed by different teams using different methods. You place them side by side and one says 8, while the other says 8, 9. At first you assume one must be off, but then you test them again, and again, and again, and every test says both clocks are working. At that point, the problem is no longer the clocks. The problem is your understanding of time. That is roughly what happened here. For a long time, scientists assumed the disagreement would fade with better data. Instead, better data made the contradiction harder to escape. And once that happened, the conversation changed. This stopped being a question of which team made the mistake. It became a question of what assumption inside our model is broken. That shift matters because modern cosmology is built on a framework called lambda CDM. This is the standard model of cosmology. It includes dark matter. It includes dark energy. It includes the overall expansion history of the universe from the Big Bang to today. And for years, Lambda CDM has been astonishingly successful. It explains the large-scale structure of the universe. It matches the cosmic microwave background extremely well. It predicts galaxy clustering patterns with impressive accuracy. It is not some weak theory hanging by a thread. It is the dominant framework because it has earned that position. Which means if the Hubble constant problem really is exposing a failure in that framework, then this is not the collapse of a bad theory. It is a crack inside one of the best theories we have, and that is much more serious. The slow rise of the crisis. This disagreement did not explode overnight. It grew gradually. In the early years, the error bars were wide enough that people could still hope the two measurements would overlap with better precision. But over time, the measurements sharpened. The early universe side got stronger thanks to missions like Planck, which measured the cosmic microwave background with extraordinary precision. The late universe side got stronger through improved observations of Cepheid variables and supernovae, especially from teams led by researchers such as Adam Rees. As the years passed, the statistical significance of the disagreement increased. At first, it looked like a mild tension, then a stronger one, then something harder to dismiss. Eventually, the discrepancy crossed the threshold that physicists often use to distinguish a curiosity from a genuine discovery. That is the point where random chance becomes an extremely weak explanation. And once it reached that stage, the phrase Hubble tension became almost too gentle, because tension sounds temporary. This no longer felt temporary. It felt structural, a universe split by time. What makes the problem even stranger is that the split is not random. This is not a case where measurements scatter in every direction. Instead, the pattern is remarkably clean. Methods tied to the early universe tend to agree with each other. Methods tied to the late universe tend to agree with each other. And the conflict is between those two eras. That is a very strange kind of disagreement, because it suggests that the issue may not be in the instruments at all. It may be in the story we tell about how the universe evolved from then to now. In other words, something may have happened during cosmic history that our model does not include. Something that changes the expected expansion rate between the time of the cosmic microwave background and the present day. And that possibility opens the door to much bigger questions. Could dark energy be changing over time? Could there be new particles affecting the early universe? Could gravity behave differently on cosmic scales than we assume? Could the standard model of cosmology be missing an entire ingredient? Those are not fringe questions anymore. They are now part of the main discussion. And that brings us to the telescope that many hoped would settle this. Instead, it made the problem even harder to escape. The telescope that was supposed to help. When the James Webb Space Telescope launched, cosmologists immediately saw an opportunity. One of the biggest criticisms of the local universe measurement involved a technical problem called crowding. The idea was simple. If you are trying to measure a Cepheid variable star in a distant galaxy, nearby stars can blur together in the image. That blending can make the target appear brighter than it really is. And if the star looks brighter than it should, it may seem closer than it actually is. That would affect the distance ladder and could artificially push the measured expansion rate higher. This was a reasonable concern, a serious one. And James Webb, with its extraordinary resolution and infrared capabilities, was supposed to test it directly. If crowding was the hidden flaw, JWST should have exposed it. Instead, JWST did something worse. It confirmed that the local measurements were holding up. The stars were cleaner than expected. The distances remained consistent. The higher expansion rate stayed in place. That result mattered because it removed one of the most credible escape routes. For years, skeptics of the higher local value could say there may be a hidden systematic error in the Cepheid measurements. But JWST made that argument much harder to maintain. And once that happened, the Hubble tension looked less like a data problem and more like a real physical inconsistency. That was one side. Then the other side got reinforced too. The other side refuses to move. If JWST strengthened the late universe case, measurements of the early universe continued to strengthen the low-value side. The ancient light measurements were not all resting on one fragile result from one old instrument. They were being checked through different analyses and independent observations, including work associated with the Atacama Cosmology Telescope. And that matters because it means the early universe side is not easy to dismiss either. So now both doors were closing. The nearby universe still said the expansion rate is high. The early universe still said it should be lower. And neither side was collapsing under scrutiny. At that point, cosmologists were forced into a much less comfortable position. Because if both measurements are genuinely sound, then something inside the standard cosmological model is missing. And if that model is missing something, then the implications reach far beyond one number. They touch the age of the universe. By this point, the Hubble tension was no longer a curiosity. It had become something far more dangerous. Because in science, a mystery can survive for a long time as long as there is still an obvious place for it to hide. A calibration issue, a biased sample, an overlooked statistical effect, a weak link in the method. As long as one of those exits remains open, researchers can tell themselves the problem is temporary. But this story changed when those exits began to close one by one. That is what made the situation feel different, not because scientists had suddenly become more dramatic, not because one press release declared a revolution, but because every time a new instrument arrived to test one side of the disagreement, that side kept surviving. And survival matters. In cosmology, the most dangerous result is not a surprising result that appears once. It is a surprising result that refuses to die. That is what was happening here. The standard model of cosmology still worked beautifully in many areas. It still described the large-scale universe with astonishing success. But in the middle of that success sat a growing contradiction that better observations were not fixing. They were sharpening it, and that is when the mood in the field began to shift. At first, researchers spoke as if the Hubble tension were an inconvenience. Then they treated it as a technical challenge. Then, slowly, more of them started speaking about it as a genuine sign that new physics might be needed. That transition did not happen because one side won. It happened because neither side lost. The ladder to the modern universe. To understand why the local measurement remained so stubborn, we have to look more carefully at the method behind it. Astronomers often call it the cosmic distance ladder, and the name is more literal than it sounds. You cannot measure the universe all at once. You measure it in steps. First, you find the distances to objects close enough to study directly. Then you use those objects to calibrate brighter objects farther away. Then you use those brighter objects to measure even larger distances. Each rung supports the next. It is elegant, but it is also delicate. If one rung is wrong, the entire structure above it can lean. That is why critics focused so much attention on it. The ladder begins with relatively nearby stars whose distances can be measured through parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. That shift can be measured, and from it astronomers can calculate distance. Once those distances are known, astronomers use them to calibrate Cepheid variable stars. Cepheids are enormously important because they pulse in brightness at a predictable rate. The longer the pulse period, the brighter the star truly is. So if you measure the rhythm of a Cepheid, you can infer its true brightness. Then, by comparing that true brightness to how bright it looks from Earth, you can determine how far away it is. That makes Cepheids one of the most valuable tools in astronomy. They are bright enough to be seen in other galaxies. They behave in ways scientists understand well. And for decades, they have served as one of the key bridges between local stellar measurements and the wider universe. Then comes the next rung, Type Ia supernovae. These explosions are so bright that they can outshine entire galaxies for a brief time. More importantly, they are consistent enough to be used as standard candles, objects whose true brightness can be estimated reliably. Cepheids help calibrate the distances to galaxies that host Type Ia supernovae. Then those supernovae, visible across vast cosmic distances, extend the ladder much farther into space. And once you know how far away those galaxies are, you compare that distance with how much their light has been redshifted by cosmic expansion. That gives you a direct estimate of how fast the universe is expanding now. Simple in principle, difficult in practice, and incredibly powerful if done well, which is exactly why the entire field kept asking the same question: was there a hidden flaw somewhere in the ladder, where people expected it to break? There were many possible weak points. Maybe Cepheids in distant galaxies were being contaminated by neighboring light. Maybe dust was distorting brightness measurements. Maybe the environments of different galaxies subtly changed the behavior of the stars being used as calibrators. Maybe the supernovae themselves were not as uniform as researchers believed. Maybe selection bias was nudging the final number upward. These were not desperate objections. They were serious scientific questions, and for a while they offered a comforting possibility. Perhaps the high local value was not revealing new physics. Perhaps it was simply the result of a measurement system so intricate that even tiny unrecognized effects were enough to create a false discrepancy. That would have been the easy answer. Complicated, yes. Embarrassing, maybe. But still manageable. Because if the distance ladder was the problem, then the universe itself could remain intact. The theory would survive. The contradiction would shrink. The standard cosmological picture would breathe again. But then came better measurements, better instruments, and repeated tests. And instead of collapsing, the ladder kept standing. Why JWST mattered so much. The James Webb Space Telescope was not built specifically to solve the Hubble tension. Its mission is much larger than that. But when it became operational, one of the most immediate questions was whether it could test the most vulnerable part of the local measurement. That vulnerability was crowding. In distant galaxies, stars can appear so close together in telescope images that their light overlaps. If astronomers think they are measuring one Cepheid cleanly, but are actually seeing blended light from nearby stars, the Cepheid could appear brighter than it really is. That matters because brightness is used to infer distance. A star that seems brighter appears closer. A galaxy that seems closer changes the calibration of the ladder, and that shifts the estimated expansion rate. So this was not a small technical concern. It was one of the strongest reasons to suspect that the local estimate might be artificially high. Webb was perfect for testing it. Its infrared sensitivity allowed it to look through dust more effectively. Its sharp vision allowed it to separate sources more clearly. If hidden crowding was distorting the Cepheid data, Webb had the power to expose it. A lot of people quietly hoped that it would, not because they wanted the local teams to be wrong, but because the alternative was worse. If JWST confirmed the local measurement, then one of the cleanest escape routes would disappear. And that is exactly what happened. Instead of revealing a fatal flaw, Webb largely supported the Cepheid-based calibration. The stars looked cleaner, the measurements held together, the higher local value remained. That did not prove that every systematic issue had vanished forever. Science rarely works that way, but it made the simplest criticism much weaker. And in a problem like this, weakening the easy criticism changes everything. Because the burden begins to move. The question is no longer, what did the observers mess up? The question becomes, what is missing from the model? When confirmation becomes a threat, this is one of the strangest moments in any scientific crisis. Normally, confirmation is reassuring, but here, confirmation was destabilizing. Every time a local measurement survived scrutiny, it became harder to preserve the larger theoretical framework without change. That is because the Hubble tension was never just about one number. It was about consistency. If the local universe says one thing and the early universe says another, then the issue is not merely that one estimate differs from another. The issue is that our story of how the universe evolved across 13.8 billion years may be incomplete, and the more reliable both sides became, the more dangerous the contradiction looked. Imagine mapping a journey using two independent records. One is a video of the departure point. The other is a direct observation of the destination. Each record is precise. Each looks trustworthy. But when you reconstruct the path between them, the traveler could not possibly have followed the route your model says they took. That does not mean the departure video is fake. It does not mean the destination is fake. It means the journey itself involved something your map does not include. That is the shape of the Hubble tension. The early universe appears to be telling the truth. The late universe appears to be telling the truth. But the path connecting them may be missing a chapter. The ancient light still said no. If the local side had been the only stubborn result, theorists could still have treated the problem as mostly observational. But the early universe side was not weakening either. That side comes from a very different source of information. The cosmic microwave background, the faint radiation left behind from the early universe. This light is often described as the afterglow of the Big Bang, though that phrase can be a little misleading. It is more accurate to say that it is the oldest light we can see directly, released when the hot early plasma cooled enough for atoms to form and light to travel freely through space. That happened when the universe was only around 380,000 years old. The cosmic microwave background carries a map of tiny temperature fluctuations, and those fluctuations encode extraordinary information. The densities of matter and radiation, the geometry of space, the contents of the universe, and the conditions from which galaxies later grew. By fitting those patterns within the standard cosmological model, scientists can infer what the present-day expansion rate should be, and that inferred value is consistently lower than the local one. This method is very different from the distance ladder. It depends on different observations, different assumptions, and different kinds of error, which means one method cannot easily contaminate the other. That is important. Because when two independent strategies disagree, the disagreement becomes much harder to dismiss as routine noise. Then other experiments entered the picture, including the Atacama Cosmology Telescope, helping confirm that the low-value picture from the early universe was not resting on one fragile foundation. So now the problem had structure. The local universe kept supporting the high value, the early universe kept supporting the low value, and independent checks on both sides kept making retreat harder. At some point, scientists had to admit something uncomfortable. The data were not converging. They were organizing themselves into two camps, a disagreement separated by cosmic time. That detail is easy to miss, but it may be the most important one in the entire story. The disagreement is not random. It is not that every measurement technique produces a different answer. It is that measurements associated with one era of cosmic history tend to cluster together, while measurements associated with another era cluster somewhere else. That pattern suggests the universe may not be mismeasured. It may be misdescribed. Something may have changed between the early universe and the present in a way the standard model does not capture correctly. And once you start thinking that way, the range of possible explanations changes dramatically. Maybe there was a brief episode of extra energy in the young universe. Maybe some unknown particle altered the expansion history before the cosmic microwave background fully imprinted its signal. Maybe dark energy is not constant after all. Maybe gravity itself behaves differently across immense distances. Maybe the contents of the cosmos are slightly richer than the current model allows. These ideas are not equally strong. Some are elegant but fail under detailed testing. Others solve one problem only by creating three more. But the important point is that the tension has pushed cosmologists into territory that would once have sounded speculative. Because when the numbers stop agreeing, speculation is no longer a luxury. It becomes part of the job, the psychological shift inside the field. Scientific revolutions are often imagined as loud, sudden events. A paper appears, a theory falls, a new one rises. Reality is usually slower. Most of the time, a field changes emotionally before it changes officially. Researchers become more cautious with old assumptions. Conference talks start using different language. Papers begin including phrases like possible evidence for new physics, where they once emphasized systematic uncertainty. People who were once certain start sounding less certain. That kind of change matters. And the Hubble tension produced exactly that kind of atmosphere, not universal agreement, not a dramatic collapse of consensus, but a growing recognition that the problem had survived too much scrutiny to be treated lightly. This is one reason the story captured so much attention beyond astronomy, because it sits at the edge between two very different possibilities. On one side lies a prosaic ending, hidden systematics, subtle bias, patient correction, case closed. On the other lies something much bigger, a real gap in the standard model of cosmology. The problem is that the data kept pushing the field away from the first possibility without yet delivering a clean version of the second. And that is the most unnerving kind of scientific situation. Not one where everything falls apart, but one where the old picture remains powerful, the new picture remains incomplete, and reality keeps refusing to simplify. The model that still worked too well to abandon. This is what makes the Hubble tension so difficult. If lambda CDM were failing everywhere, replacing it would be easy. If it were collapsing across multiple fronts, everyone would already know a new framework was needed. But that is not what happened. The model still explains an enormous amount. It still matches the cosmic microwave background astonishingly well. It still describes large-scale structure with impressive accuracy. It still gives a coherent account of the universe from early times to the present in many areas. So cosmologists are trapped in an awkward position. They have a model that works too well to discard, but not cleanly enough to trust without question. That is a dangerous place for any theory, because once a model becomes both indispensable and suspect, every new observation carries double weight. If the data agree, the model survives. If the data disagree, the contradiction deepens. That is why so much attention shifted toward new independent methods. Researchers needed ways to measure the expansion rate that did not rely entirely on the classic distance ladder and did not rely entirely on early universe inference. They needed something else, something that could act like a third witness, and that is exactly where the story began to expand, because the universe offers more than two ways to interrogate its history. There are other signals, other rulers, other explosions, other structures written across space, and each of them brings the same question back into focus. How fast is the universe really expanding? By the time those new methods started maturing, the Hubble tension was no longer just a disagreement between Cepheids and the cosmic microwave background. It was becoming a full-scale test of whether modern cosmology understood its own timeline. And in the next part, that is where we go next. Because once new methods entered the picture, methods involving gravitational lenses, giant galaxy maps, and entirely different kinds of cosmic measurement, the story did not become cleaner. By now, the universe had split into two stories. One came from the earliest light in existence. The other came from the modern cosmos, measured rung by rung through stars and supernovae. And the most troubling part was not that these two stories disagreed. It was that both of them kept surviving attack. That is the moment when science starts looking for a third witness. Because if two methods disagree, the natural response is not immediately to throw out the theory or declare a revolution. The responsible response is to ask a harder question. Is there another way to measure the same thing? Another method, another data set, another physical process, something independent enough that it does not inherit the same weaknesses. If that third witness sides clearly with one camp, the path forward becomes easier. But if the third witness gives an answer somewhere in between, or opens an entirely new line of uncertainty, then the crisis deepens. That is exactly what began to happen. The Hubble tension stopped being just a fight between the distance ladder and the cosmic microwave background. It started becoming a wider investigation into the expansion history of the universe itself. And once that happened, the field entered a far more dangerous phase, because the more independent methods you bring in, the less you are testing an instrument. You are testing reality. Why a third method matters so much. There is a reason scientists were desperate for new approaches. The classic local measurement and the classic early universe measurement were both powerful, but they each came with baggage. The distance ladder depended on multiple calibrations stacked on top of one another. That made it direct, but structurally delicate. The cosmic microwave background, on the other hand, did not measure the present-day expansion rate directly. It inferred it by fitting the early universe through the standard cosmological model and then projecting forward. That made it elegant and precise, but also model-dependent. So critics on both sides had room to argue. People skeptical of the distance ladder could point to hidden systematics. People skeptical of the early universe value could point to the possibility that the model being used to interpret the ancient light was incomplete. That is why new methods mattered. They offered a chance to escape the old argument, not by repeating the same measurement more loudly, but by measuring the universe through completely different physics. This was not just about getting more data. It was about changing the angle of attack. The universe has other measuring tools. Astronomy has a strange advantage. We cannot touch the stars. We cannot rerun the Big Bang. We cannot build a laboratory large enough to recreate cosmic history, but the universe itself leaves clues in many forms: exploding stars, ripples in ancient light, the clustering of galaxies, the warping of light by gravity. The pattern of matter stretched across billions of light years. Each of these becomes a kind of instrument, and over time, cosmologists developed more ways to use those instruments to estimate the expansion history of the cosmos. Some of these methods were not yet precise enough to settle the Hubble tension on their own, but that did not make them unimportant. Even an imperfect third witness can be critical. Because if several independent methods begin leaning in the same direction, the probability that the whole crisis is just an accident starts to shrink. And if they refuse to line up cleanly, that tells you something too. It tells you the problem may be more fundamental than anyone hoped. Gravitational lenses and delayed light. One of the most fascinating independent approaches came from gravitational lensing. This method sounds almost like science fiction, but it follows directly from Einstein's theory of gravity. Mass bends spacetime, and when light passes near a massive object, its path bends too. That means a massive galaxy sitting between Earth and a much more distant light source can act like a lens. It can warp, magnify, and even split the background light into multiple images. In some cases, the distant object is something variable, like a quasar, an extremely bright active galactic nucleus whose light flickers over time. Now imagine that light taking several different paths around a foreground galaxy before reaching us. Those paths are not all the same length. Some are longer. Some pass through regions with slightly different gravitational structure. So when the distant quasar brightens or dims, Earth does not see the change in all images at once. It arrives with delays. That delay becomes incredibly useful. If you can measure the timing differences between the images, and if you can model the mass distribution of the lensing galaxy accurately enough, you can estimate cosmic distances and infer the expansion rate of the universe. This is remarkable because it has very little to do with Cepheids or the cosmic microwave background. It is a different window entirely, and some of these lensing-based measurements tended to support the higher, local universe-style value. That did not end the debate, because lensing analyses bring their own modeling challenges, but it mattered. It meant the distance ladder might not be standing alone. For people who hoped the tension would vanish once enough alternative methods appeared, this was not comforting. It was unsettling, because every new independent hint in favor of a higher value made the contradiction harder to isolate. The problem with middle answers. At first glance, an intermediate result might seem helpful. If a third method gives an answer somewhere between the low early universe value and the high local value, that might sound like a compromise. But in science, compromise is not always clarity. Sometimes a middle answer simply means the uncertainties are still too large to identify the truth cleanly. Sometimes it means the method is not yet mature enough. And sometimes it means the situation is more complicated than a clean two-sided battle. That was part of the frustration. Some independent methods leaned high. Some were broadly compatible with both sides within their uncertainties. Some added confidence without fully resolving anything. So instead of immediately acting like a judge, these third witnesses often behaved more like additional interrogators. They did not close the case, they expanded it, and that expansion changed the feeling of the field. Because once multiple independent methods enter the story, the question stops being, which technique is flawed? It becomes, what pattern is the universe trying to reveal? Standard sirens and cosmic sound. Then there was another idea, one that sounded almost poetic. If ordinary astronomy gives us light, then gravitational wave astronomy gives us something more like vibration. When massive objects such as neutron stars collide, they send ripples through spacetime itself. These are gravitational waves, and when detectors observe them, the signal carries direct information about the distance to the source. That is why some scientists call them standard sirens. Unlike standard candles, which rely on light and brightness, standard sirens use the waveform of spacetime ripples to estimate distance. If astronomers can also identify the host galaxy of the event and measure its redshift, they have another way to infer the expansion rate of the universe. This method is extraordinarily exciting because it is independent in a very deep way. It does not depend on Cepheid variables. It does not depend on supernova calibration in the traditional sense. It does not depend on reading the early universe through the standard cosmological model. It is its own route through the problem. The challenge is that gravitational wave cosmology is still young. The number of events useful for this purpose has been limited, and the uncertainties are still broader than what would be needed to decisively settle the Hubble tension. But that is not the point. The point is that the universe keeps offering new ways to check the same story, and each new check raises the stakes. Because if the disagreement survives across many methods, then the chance that we are looking at a simple observational mistake grows smaller. The expansion history may not be smooth. This is where the story becomes conceptually harder. For a long time, many discussions about the Hubble tension were framed as if there were only two possibilities. Either one of the measurements is wrong, or the standard model needs new physics. But the phrase new physics covers a huge landscape. It does not mean one obvious replacement is waiting just off stage. It means many possible modifications, each with consequences. Some proposals suggested a brief injection of extra energy in the early universe, often called early dark energy. The idea was that the young cosmos may have gone through a short phase in which an additional energy component slightly changed the expansion history before fading away. This could help reconcile the inferred value from the cosmic microwave background with the higher value measured locally. At least in principle, the attraction of this idea was clear. It did not require rewriting everything about the universe. It only required adding a temporary ingredient at the right moment in cosmic history. But ideas that sound elegant in summary often become harder under full testing. A model must not only help with the Hubble constant, it must also remain consistent with the cosmic microwave background, galaxy clustering, large-scale structure, and other precision observations. That is where many proposed fixes begin to struggle. A model solves one tension and creates another. It eases one contradiction but worsens a different measurement. It looks promising in theory and unstable in detail. This has happened again and again, and it is one reason the Hubble tension remains so compelling. The universe is not merely resisting explanation, it is resisting easy explanation. The maps written in galaxy clustering. Then another major line of evidence continued growing. Large surveys of galaxies across the sky. These surveys do not just count galaxies. They map patterns in how galaxies cluster across space, and those patterns preserve traces of the early universe. One of the most important of these traces is called baryon acoustic oscillations. In the early universe, matter and radiation were tightly coupled in a hot plasma. Pressure waves moved through that plasma, leaving an imprint on the distribution of matter. After the universe cooled and the plasma became neutral, that pattern froze into the large-scale structure of the cosmos. As galaxies later formed, they inherited that subtle preferred scale. Today, astronomers can measure it statistically by mapping huge numbers of galaxies. That scale acts like a standard ruler written across the universe. By observing how that ruler appears at different distances and times, scientists can reconstruct aspects of the expansion history. This is powerful because it provides another route into the cosmic timeline, one that connects early conditions to later structure in a measurable way. And as galaxy surveys improved, they added more precision to our picture of how the universe expanded over billions of years. But again, the result was not a simple rescue. Instead, the evidence kept tightening the constraints around possible solutions. That sounds helpful, and in one sense it is, but it also creates pressure. Because once the available space for explanations starts shrinking, you can no longer solve the problem with vague new physics. You need something specific enough to survive all the existing data. And specificity is where many ideas fail. When more data does not mean more comfort. There is a comforting myth about science that more data always makes things cleaner. Sometimes it does. Sometimes more data only proves that the mess is real. That is what makes this story so gripping. Each new line of evidence was supposed to help narrow the uncertainty, and it did. But narrowing the uncertainty did not necessarily narrow the crisis. In some cases, it intensified it. The third witnesses did not arrive as saviors. They arrived as pressure. Pressure on the local side to prove its measurements were truly solid. Pressure on the early universe side to justify the model assumptions behind its inference. Pressure on theorists to invent explanations that did not collapse under the weight of all the other cosmological evidence. And as that pressure increased, one truth became harder to avoid. The Hubble tension was not living in one corner of astronomy anymore. It was spreading through the logic of cosmology itself. This is where DESI enters the story. By the time the field reached this stage, another enormous project was beginning to reshape the conversation. That project was DESI, the Dark Energy Spectroscopic Instrument. DESI was built to map the universe on a staggering scale, measuring the redshifts of tens of millions of galaxies and quasars. Its purpose was not simply to count objects, but to chart the structure of the cosmos with extraordinary precision and use that structure to study the history of expansion. That matters because once you can trace the distribution of matter across vast stretches of time, you gain a sharper picture of how cosmic acceleration has behaved. And that leads straight into one of the most dangerous questions in modern cosmology. What if dark energy is not as simple as we thought? For years, the standard model treated dark energy as something essentially constant, a built-in property of space, often represented by the cosmological constant, lambda. That assumption is elegant. It is mathematically convenient, and for a long time it worked. But if the expansion history of the universe has not been as smooth and simple as lambda CDM assumes, then dark energy becomes one of the first suspects. DESI did not enter the story as a magic solution. It entered as a machine for making the story harder to ignore. Because once galaxy maps become precise enough, they do not just offer more numbers. They start testing whether the underlying shape of the standard cosmic story still fits. And that is where the Hubble tension begins to overlap with something even larger, not just a disagreement over today's expansion rate, not just a mismatch between early and late measurements, but a growing suspicion that the force driving cosmic acceleration itself may not be behaving the way we assumed. That possibility changes everything. Because if dark energy evolves, then the timeline of the universe evolves with it. And if the timeline evolves, then the bridge between the early universe and the present may need to be rewritten. That is not a calibration fix. That is a structural rewrite. The tension stops being isolated. This is how scientific crises become dangerous. At first, the Hubble tension looked like a narrow crisis, a disagreement in one number a conflict between two ways of measuring the same universe, a technical issue perhaps, a frustrating one but contained. But the longer the problem survived, the less contained it looked, because the universe has a way of turning one unanswered question into a doorway for several more. And once DESI entered the picture, that doorway opened wider. The problem was no longer just about how fast the universe is expanding today. It was becoming a question about whether the force believed to be shaping the long-term expansion of the universe, dark energy, has been understood correctly at all. That is where the story turns from unsettling to dangerous, because for years, dark energy had occupied a strange position in cosmology. It was mysterious, yes, but it was also stable, at least on paper. Scientists did not know what dark energy truly was in a fundamental sense, but within the standard cosmological model, it behaved in a very simple way. It acted like a constant property of space itself. As the universe expanded, dark energy remained effectively uniform, driving cosmic acceleration in a way that was mathematically clean and observationally useful. That simplicity was one of the reasons lambda CDM became so successful. It may not have explained everything, but it explained enough with remarkable precision. So if dark energy was no longer behaving like a constant, then the consequences would stretch far beyond one tension in one measurement. They would strike at the framework holding the modern cosmic story together, the ingredient we still do not understand. Dark energy is one of the most extraordinary ideas in science because it is both central and deeply unknown. Astronomers did not invent it for fun. They introduced it because the universe forced them to. In the late 1990s, observations of distant Type Ia supernovae revealed something shocking. The expansion of the universe was not slowing down under gravity as many expected. It was speeding up. Some force or some property of spacetime was driving galaxies apart faster over time. To account for that acceleration, cosmologists returned to an idea associated with Einstein's cosmological constant, a term that can be understood as the energy of empty space itself. That became the simplest version of dark energy, and for a while it worked astonishingly well. You add dark matter, you add ordinary matter, you add radiation, you add a cosmological constant, and suddenly an enormous amount of the observable universe starts making sense. That is the elegance of lambda CDM, but elegance can become a trap, because once a simple model starts fitting many observations, there is a temptation to treat its unknown pieces as settled enough. Dark energy was never really settled. It was only behaving itself, and if new data suggested it might not be constant after all, then one of the most convenient assumptions in cosmology would move from working placeholder to possible mistake. What DESI was built to do. DESI, the Dark Energy Spectroscopic Instrument, was built to study the large-scale structure of the universe with extraordinary precision. That description can sound abstract, but the mission is brutally concrete. Measure the positions of galaxies, measure their redshifts, map them across cosmic time, use those maps to reconstruct how the universe expanded. DESI does this on a vast scale, collecting light from millions upon millions of galaxies and quasars. Each spectrum provides a redshift. Each redshift helps place an object in the three-dimensional history of the cosmos. And once enough of those measurements are gathered, the universe starts to reveal its pattern, not as isolated points, but as structure, filaments of galaxies, voids, clustering. The leftover imprint of ancient sound waves frozen into matter. Those patterns are not random. They preserve information about the expansion history of the universe and about the physical ingredients shaping that history. That is why DESI matters so much in this story. It is not merely another telescope checking one disputed number. It is a machine for testing whether the standard narrative of cosmic expansion still fits the shape of reality when measured at enormous scale. And if it does not fit perfectly, the question becomes unavoidable. What exactly is changing? The ruler left behind by the early universe. One of DESI's most powerful tools involves something called baryon acoustic oscillations. The term sounds technical, but the core idea is surprisingly beautiful. In the early universe, matter and radiation were mixed together in a hot plasma. Pressure waves moved through that plasma, somewhat like sound waves moving through air. Those waves pushed matter outward in subtle patterns. Then the universe cooled, atoms formed, light decoupled from matter, the plasma phase ended. But the imprint of those ancient waves remained. It became frozen into the large-scale distribution of matter, leaving behind a preferred scale, a kind of cosmic ruler. Billions of years later, when astronomers map vast numbers of galaxies, they can still detect that statistical imprint in how galaxies are spaced. That ruler can be used to measure the geometry and expansion of the universe at different epochs. This is extraordinarily powerful because it connects the early universe to the later one through structure itself. It does not rely on the same assumptions as the distance ladder. It does not ask us to trust only one local calibration chain. And it does not simply repeat the cosmic microwave background story in exactly the same form. Instead, it acts as another deep consistency check on cosmic history, which is why DESI became so important and why its results immediately entered the broader argument. When dark energy starts drifting, for a long time, the simplest assumption was that dark energy is constant. That is the lambda in lambda CDM. It does not strengthen, it does not weaken, it does not evolve in a dramatic way over time. It simply remains there, shaping expansion as space grows. If that is true, the mathematics of cosmic expansion follow a relatively stable path. But if dark energy changes over time, even slightly, then the expansion history also changes. That matters because the Hubble tension is fundamentally about connecting different moments in cosmic time. The early universe says one thing, the late universe says another, and the bridge between them may be wrong. A changing dark energy component is one possible way to alter that bridge, not the only one, not automatically the correct one, but one of the most consequential. Because if dark energy evolves, then it is not merely an unexplained constant. It is dynamic. And a dynamic dark energy would mean the standard model is missing behavior that directly affects the history and possibly the fate of the cosmos. That is the kind of change that reaches everywhere. Why this is bigger than one tension. It is tempting to imagine cosmology as a set of separate puzzles, one puzzle for the Hubble constant, one for dark matter, one for dark energy, one for galaxy formation. but reality may not respect those categories. Sometimes what looks like one isolated discrepancy is actually a symptom of something larger underneath. That is why DESI's role in this story feels so important. It raises the possibility that the Hubble tension is not a lonely outlier. It may be part of a broader discomfort in the standard model. If cosmic acceleration is not described perfectly by a constant dark energy term, then that could affect how we connect early universe inference to present-day expansion. It could influence the timeline, the calibration of our expectations, and the way multiple probes line up. In that sense, DESI did not simply add more data. It raised the level of suspicion, not suspicion that everything is wrong, but suspicion that the standard picture may be too rigid for the universe it is trying to describe. The danger of a model that almost works. This is the central tension in modern cosmology. The standard model is not failing dramatically. It is not collapsing on every front. It is not being humiliated by every new observation. It is doing something far more complicated. It is continuing to work extremely well in many areas while producing a few persistent fractures that refuse to heal. That is a much more difficult situation for science. When a theory fails everywhere, the response is obvious. When a theory succeeds everywhere, the response is also obvious. But when a theory explains most of reality and still leaves behind a small number of stubborn contradictions, researchers enter a dangerous zone. They cannot abandon the model easily. They cannot trust it completely, and every new observation becomes a test of whether the cracks are superficial or structural. That is where cosmology now finds itself. The model still predicts beautifully, but the universe is no longer cooperating cleanly. And once dark energy enters the list of suspects, the stakes rise immediately, because dark energy is not some minor correction term. It dominates the long-term behavior of the cosmos. If it is drifting, then the future of the universe may also be drifting with it. What a changing dark energy would really mean. If dark energy is not constant, then one of the most basic assumptions about the expansion history of the universe becomes provisional. That would mean the story from the Big Bang to the present is not just incomplete in detail. It is incomplete in structure. The age of the universe might need to be reconsidered in subtle ways. The rate of cosmic acceleration across different eras might need refinement. The way large-scale structure formed might require new interpretation. And the link between early measurements and late measurements might have to be rebuilt. This is why cosmologists treat even hints of evolving dark energy with such caution. The implications are enormous, and yet caution cuts both ways. Because if the data keep pointing in that direction, then refusing to explore it becomes just as risky as embracing it too quickly. That is the balance the field has been trying to maintain. Do not overreact. Do not underreact. Do not mistake noise for revolution, but do not mistake persistent evidence for noise either. That is easier said than done. Not all cracks lead to collapse. At this point, it is important to say something clearly. A crack in the standard model of cosmology does not mean the whole structure is about to collapse. Science is not a house of cards. When a major framework is revised, most of what it explains usually remains valuable. The old model may survive as an approximation or as part of a larger theory, or as a special case under certain conditions. That is how physics often progresses. Newton was not erased by Einstein. He was absorbed into a deeper structure. In the same way, if lambda CDM is missing something important, that does not mean everything it achieved disappears. It may still be largely correct, while incomplete in a critical place. But that possibility is not comforting enough to remove the tension, because the very fact that incompleteness may exist at a foundational level means the next breakthrough in cosmology may not be a minor patch. It may require rethinking one of the central assumptions that has guided the field for decades: the uncomfortable pattern emerging. By now, a pattern was becoming difficult to ignore. The Hubble tension had survived. Independent methods had complicated rather than simplified the case. JWST had made it harder to blame local measurement error. Early universe measurements had remained strong. Large-scale structure surveys had begun testing the expansion story with growing precision. And dark energy, once treated as stable enough for practical purposes, no longer looked entirely beyond suspicion. This does not amount to proof of a new model, but it does amount to pressure. Pressure on the assumption that cosmic expansion is fully understood. Pressure on the idea that one elegant equation can smoothly connect all epochs without modification. Pressure on the belief that the remaining contradictions are merely technical annoyances waiting to disappear. Maybe they are, but fewer scientists are willing to assume that automatically now. And in science, that change in confidence matters almost as much as a formal discovery, because once confidence weakens, exploration widens. Researchers begin testing ideas that once seemed too speculative. They compare models that previously looked unnecessary. They take seriously the chance that the universe may be more dynamic, stranger, and less neatly packaged than the standard picture suggested. That is where the field has been drifting. Not into chaos, not into certainty, but into a more dangerous kind of honesty. The data may be telling us that the universe is not as simple as we hoped. The story is no longer about one number. At the beginning, the Hubble tension could be summarized in a sentence: two methods, two answers, one problem. But by now, that summary is no longer enough, because the story has expanded. It now includes the reliability of the distance ladder, the interpretation of the cosmic microwave background. Once the Hubble tension survived long enough, cosmology entered a new phase. The conversation was no longer only about measurement. It became a rescue mission. Because if the observations were not going to come back into agreement on their own, then theorists had to do something much harder. They had to ask what kind of new ingredient could be inserted into the story of the universe without destroying everything else that already worked. That is the trap. A successful fix cannot merely explain one number. It has to preserve the rest of cosmology too. It has to leave the cosmic microwave background mostly intact. It has to keep galaxy clustering under control. It has to avoid breaking the large-scale structure of the universe. It has to fit supernova data, early universe physics, and the timeline of cosmic expansion. In other words, it cannot behave like a patch on one hole if it tears three more holes somewhere else. That is why the Hubble tension became such a brutal test for theory. It invited bold ideas, then punished them. Again and again, researchers proposed solutions that looked promising at first glance. And again, those solutions ran into the same problem. The universe is connected too tightly for easy repairs. The dream of a small correction. At first, many hoped the answer would be elegant, not a total rewrite, not a revolution, just a subtle modification. Maybe some temporary energy component existed in the early universe. Maybe an unknown particle species slightly changed the expansion rate. Maybe gravity behaved just a little differently at large scales. Maybe one term in the standard model needed to breathe instead of remaining fixed. These were attractive possibilities because they preserved the basic architecture of cosmology. The Big Bang still happens, the cosmic microwave background still matters, dark matter still exists, galaxies still form more or less the way we understand them. Only one missing ingredient has to be added. That kind of solution is always appealing in science because it promises the best of both worlds, novelty without collapse. But the more precisely cosmologists tested these ideas, the more difficult that promise became to keep. Early dark energy, the most tempting fix. One of the most discussed proposals was early dark energy. The idea was simple enough to say in one sentence. What if the universe briefly contained an extra burst of energy before the release of the cosmic microwave background, and that burst slightly altered the expansion history at just the right time? That temporary contribution could change the inferred scale of the early universe and potentially help bring the low early universe Hubble value closer to the higher local measurement. This idea became so attractive because it targeted the heart of the problem. The Hubble tension is really about a mismatch between the young universe and the present one. So instead of changing the universe everywhere and always, early dark energy changes it only during a narrow window when the consequences could matter most. It is a surgical idea. That is why so many people took it seriously. At first, it almost felt like the perfect compromise. The standard model survives mostly. The early universe gets one extra ingredient. The expansion history shifts just enough, and the tension begins to soften. But the universe rarely rewards us for finding a fix that sounds neat in summary. Because once early dark energy models were confronted with the full range of precision data, the situation became harder. A model might ease the Hubble tension somewhat, but then affect other observables in uncomfortable ways. It might improve one fit while worsening another. It might require the extra energy to appear and disappear with suspiciously careful timing. That is one of the recurring dangers in theoretical cosmology. A solution can start to look less like physics and more like tuning, and tuned solutions always raise suspicion. Not because they are impossible, but because nature usually does not arrange itself to solve our parameter problems in the most convenient possible way. The curse of solving one problem at a time. This became a pattern. A theory would appear and gain attention because it nudged the Hubble constant in the desired direction. Then researchers would test it against something else. Large-scale structure, baryon acoustic oscillations, the shape of the cosmic microwave background power spectrum, the growth of matter over time, supernova constraints, gravitational lensing, and under those tests, the elegant fix would start to wobble. That is because cosmology is not built from isolated boxes. It is built from linked consequences. Change the expansion rate in one epoch, and you often change the sound horizon. Change the sound horizon, and you affect the interpretation of large-scale structure. Change the clustering of matter, and you run into galaxy survey constraints. Modify gravity, and suddenly structure growth, lensing, and expansion all begin moving together. The universe does not let you edit one line without checking the rest of the script. That is what has made the Hubble tension so difficult to solve in a satisfying way. There are many ways to move a number. There are far fewer ways to move a number without breaking reality somewhere else. New particles, dark radiation, and hidden ingredients. Another class of ideas involved adding new particles or new forms of radiation to the early universe. These proposals often sounded less dramatic than modified gravity and more technically plausible than a total rewrite of dark energy. Maybe there was an extra light particle species in the young universe. Maybe some hidden sector contributed radiation-like energy. Maybe neutrino physics was slightly richer than the standard picture assumed. In broad terms, these ideas try to alter the contents of the early universe just enough to shift the inferred expansion history. Again, the appeal is obvious. If the problem lies in the bridge between early and late times, then perhaps the early universe contains something our model has not counted properly. That is not a crazy thought. The early universe was extreme, dense, hot, violent, potentially full of physics we do not yet understand, so adding a hidden ingredient there feels reasonable. But reasonable is not the same as successful. Because extra particles or dark radiation also leave signatures. They affect nucleosynthesis, the cosmic microwave background, and the detailed pattern of fluctuations from which later structure grew. And once those signatures are compared against the data, the parameter space tends to shrink fast. That has happened many times. What looked like a wide-open theoretical possibility narrows into a very thin corridor where the idea can survive at all. And in many cases, even that corridor starts to feel strained. Modified gravity, changing the rules instead of the ingredients. Then there is the more radical route. What if the problem is not the contents of the universe, but the laws used to describe how the universe evolves? That is where modified gravity enters the story. This family of ideas asks whether Einstein's general relativity, while extraordinarily successful, might require adjustment on the largest scales in the cosmos. This is a serious question, not a fringe fantasy. General relativity has passed many tests, but most of those tests happen in environments very different from the full scale of cosmic expansion. So some theorists asked whether gravity behaves slightly differently across vast distances in ways that could influence the expansion history or the growth of structure. It is a bold move. Instead of adding a new cosmic ingredient, you alter the rules that govern the whole game. That is powerful but dangerous, because once you change gravity, the consequences spread everywhere. You do not just affect the Hubble constant, you affect how galaxies cluster, you affect gravitational lensing, you affect the evolution of cosmic structure, you affect the history of expansion from early to late times. That means modified gravity models face an even harsher standard than many other proposals. They are not allowed to be interesting only in one place. They must remain consistent across an enormous range of observations. That is why so many of them struggle. They may help in one respect, but they tend to attract constraints from many others. A theory that changes gravity enough to matter cosmologically often changes enough else to become difficult to hide. Why the standard model keeps surviving. This is the strange irony at the center of the story. Every proposed fix reveals why lambda CDM became dominant in the first place. Because the standard model is not merely popular. It is resilient. You can dislike its mysteries. You can resent how much it leaves unexplained. You can point out that dark matter and dark energy are still not understood at a fundamental level, and all of that is fair. But when you try to replace or even lightly modify the model, you immediately discover how much observational territory it already controls. That is why the model survives attacks so well. It is not elegant because it is simple in an absolute sense. It is elegant because it holds together across so many different scales and eras with so few adjustable pieces. So every failed replacement does not just disappoint theorists, it also strengthens respect for the model they were trying to improve. That is part of what makes the Hubble tension feel so unresolved. The standard model looks incomplete, but most alternatives look worse. The possibility nobody likes. There is another possibility, and almost nobody finds it satisfying. What if there is no single clean fix? What if the Hubble tension is not caused by one new particle, one episode of early dark energy, or one elegant correction to gravity, but instead reflects a more complicated mismatch between several assumptions, several measurements, and several layers of cosmic interpretation? That possibility is uncomfortable because it denies the drama of a neat ending. It suggests the universe may not be hiding one secret, it may be hiding several small ones. And if that is true, then the road forward becomes slower and messier. Perhaps part of the tension comes from subtle model incompleteness. Perhaps part comes from observational limitations. Perhaps part reflects new physics, but not in the clean form anyone hoped for. Perhaps the universe is exposing a cluster of approximations that all looked harmless until precision cosmology became good enough to trap them together. That kind of explanation is hard to love. It is much easier to imagine a breakthrough paper, one brilliant new field, one final theory. Reality is often less cinematic than that. Why theorists keep coming back anyway. And yet the search continues, because even failed ideas are useful in a case like this. Each proposal teaches researchers something about what the data will allow. Each rejected model narrows the space of viable explanations. Each failed rescue attempt reveals which parts of the cosmic story are more rigid than they first appeared. In that sense, theory is not only trying to save the standard model or overthrow it. Theory is mapping the boundaries of the possible. This matters because cosmology is reaching the point where vague explanations are no longer enough. The data have become too precise. You cannot simply say maybe new physics and leave it there. You have to say what kind, when it acts, how strongly it acts, what else it changes, and why it does not ruin the rest of the universe in the process. That is an unforgiving standard, but it is also the reason this field is so exciting right now, because every surviving idea is being tested against reality at a level that would have been impossible only a generation ago. When a crisis becomes productive, scientific crises are not always signs of failure. Sometimes they are signs that measurement has become good enough to expose the limits of old assumptions. That may be what is happening here. For decades, cosmology moved forward by turning the universe into a precision science. The parameters tightened, the surveys expanded, the maps sharpened, the error bars shrank. That success created the Hubble tension, not ignorance, not sloppiness, success. If the measurements were poor, the disagreement could hide. If the model were weak, no one would care enough to test it this hard. If the field were immature, there would not be so many independent ways to check the same history. The tension exists because cosmology became powerful enough to corner itself. And once a science corners itself, one of two things usually happens. Either the contradiction dissolves under even better work, or the science discovers that its best framework was only an approximation of something deeper. That is the threshold cosmology now stands on. The universe still has not confessed. By this point, many of the most obvious theoretical escape routes had been explored. Early dark energy looked promising, then difficult. Extra particles sounded plausible, then constrained. Modified gravity remained bold, but hazardous. Hybrid fixes helped in one place and struggled in another. And still, the core problem remained. The early universe wanted one expansion rate. The local universe wanted another. Independent methods complicated the argument instead of ending it. Dark energy had entered suspicion. And the standard model, though wounded, refused to collapse. That is what makes the situation feel so unusual. In many scientific disputes, the field gradually moves toward a likely answer. Here, the field moved toward a stronger understanding of why the easy answers fail. That is progress, but it is not comfort. It means cosmologists are learning the shape of the trap without yet knowing how to escape it. The next stage of the story. Once theory reached this point, the pressure shifted back to observation again, because if no proposed fix could yet command confidence, then the only path forward was sharper evidence, better measurements, new instruments, more independent probes, more precise maps of structure, more ways to test whether dark energy evolves, whether the distance ladder bends, whether the early universe inference holds, and whether the standard model is. There comes a point in every scientific crisis when theory stops leading the story. At first, people argue, they propose explanations, they defend old assumptions, they sketch elegant alternatives. They try to rescue the existing model with minimal changes, but eventually the room changes. The ideas are still there, the debates are still there, the papers keep coming, yet the real power begins to shift elsewhere. It shifts to observation, because once enough theories have been proposed, stretched, tuned, and tested, the field reaches a harder truth. No one gets to win this argument by sounding clever. At that point, only the universe gets the final word. That is where cosmology now finds itself. The Hubble tension has survived the stage where it could be dismissed as a temporary nuisance. It has survived the stage where easy theoretical fixes looked enough. It has survived repeated attempts to contain it inside one method, one telescope, or one hidden systematic. And so the pressure has returned to the data. Sharper data, broader data, independent data, not to decorate the argument, but to decide it. Because if the standard model of cosmology really is missing something, The next generation of observations may expose exactly where the missing chapter begins. And if the model is still fundamentally correct, then observations will have to show how the apparent contradiction dissolves. Either way, the future of this story now belongs to measurement. Why the mood in cosmology has changed. One of the clearest signs that a field is shifting is not that everyone agrees. It is that confidence starts changing shape. For years, many scientists viewed the Hubble tension with a kind of disciplined skepticism. That skepticism was reasonable. Precision cosmology is hard. Tiny biases can matter. Extraordinary claims should not be embraced too early, but skepticism evolves. At first it asks, is this real at all? Later it asks, if this is real, what does it mean? That is a very different question, and more researchers have begun living in that second question, not because the answer is obvious, not because the standard model has already failed, but because the contradiction has lasted too long under too much scrutiny to be treated like a passing nuisance. This does not mean the field has declared a revolution. It means the field is less certain that no revolution is needed. That distinction matters. Science almost never changes in one dramatic motion. It changes through an accumulation of pressure until the old confidence no longer feels automatic. That is the stage cosmology seems to be entering now. The dangerous power of repeated confirmation. There is something uniquely destabilizing about repeated confirmation when the confirmed result is itself a problem. Every new dataset that strengthens one side of the Hubble tension does more than improve precision. It removes excuses. If the local measurement keeps surviving, then blaming it on sloppy calibration becomes harder. If early universe inferences keep surviving, then dismissing them as fragile modeling becomes harder. If independent methods continue leaning in meaningful directions, then the space for denial keeps shrinking. That is why recent observations have felt so important. They have not simply added more numbers. They have increased the cost of pretending the disagreement is trivial. And once a disagreement becomes too expensive to ignore, the whole field begins reorganizing around it. Research priorities shift. New surveys become more valuable. Independent probes become more urgent. Theoretical speculation becomes more constrained. In that sense, the Hubble tension is no longer just a scientific puzzle. It is becoming an organizing pressure in cosmology itself, the era of cross-checking everything. Modern cosmology is entering a phase where no single measurement gets to stand alone for long. That is one of the greatest strengths of the field. Every result is cross-examined by something else. A distance estimate can be checked against another ladder. An expansion history can be tested against galaxy clustering. A model fitted to the cosmic microwave background can be compared with late-time structure, lensing, supernovae, and redshift surveys. This is what makes the current moment so powerful. The question is no longer whether one team can produce one impressive result. The question is whether reality stays consistent when watched from many directions at once. That is much harder to fake, much harder to misunderstand, and much harder to simplify. This also means the next breakthroughs may not arrive as one spectacular discovery. They may come as a convergence of many smaller results. A stronger lensing constraint here, a tighter galaxy survey there, a better supernova calibration, a cleaner gravitational wave distance estimate, a more detailed mapping of cosmic expansion across time. Each one adds pressure, and eventually pressure becomes verdict, why new observations matter more than new opinions. At a certain point, cosmology does not need more confidence, it needs discrimination. It needs observations that can clearly distinguish between possibilities that currently remain too close to separate. Does dark energy evolve or not? Is the local expansion rate truly high or only apparently high? Is the sound horizon from the early universe being interpreted correctly? Are we missing an ingredient in the young cosmos, the later cosmos, or the link between them? These are not questions that can be settled by preference. They need better evidence. That is why the newest observational programs matter so much. They are not merely collecting data, they are narrowing the menu of acceptable realities. And that is a frightening thing for a field built on a successful standard model. Because once the menu narrows enough, cosmologists may be forced to accept an answer they do not fully like. Either the tension will weaken in a specific, observable way, or it will harden into a case for incompleteness that becomes harder and harder to avoid. Both outcomes are dramatic. One preserves the old structure after years of anxiety. The other opens the door to a deeper universe than the standard model currently describes. The standard model is now being stress-tested in public. For decades, Lambda CDM was the quiet success story of cosmology. It did not have the cultural fame of black holes or the Big Bang, but inside the field, it was the backbone. Now that backbone is being stress-tested more openly than ever. This does not mean it is broken. It means it is under examination in a way that no good scientific framework can escape forever. And honestly, that is healthy. A model becomes powerful by surviving scrutiny, not by avoiding it. The problem is that some forms of scrutiny do not merely confirm a theory. They reveal the edges of its usefulness. That possibility now hangs over Lambda CDM. Maybe it will emerge stronger, with the tension eventually explained through some subtle but non-revolutionary correction. Maybe it will survive only as an approximation, still useful but no longer fundamental. Maybe it will hold in broad outline while requiring one major new ingredient to account for the observed universe cleanly. Those are very different futures, but observation is beginning to force cosmology toward one of them. What if the universe really has been hiding new physics? This is the question that gives the whole story its electric charge. Not because new physics is a magic phrase, not because scientists are desperate for drama, but because new physics is what becomes thinkable when old physics remains impressive and yet incomplete. If the Hubble tension is real in the deepest sense, then the implications could be profound. Maybe the early universe contained an ingredient that no current particle model fully describes. Maybe dark energy is dynamic rather than constant. Maybe the relationship between matter, expansion, and gravity changes over cosmic scales. Maybe the standard cosmological story is missing a transitional phase that current textbooks glide past too smoothly. Any one of those would matter enormously, because cosmology is not just about distant galaxies. It is about the operating rules of reality at the largest scale we can observe. So if the model guiding that scale is incomplete, The correction would not be cosmetic, it would be foundational. And that is what makes this moment so unusual. The data are not merely asking whether one number should be 67 or 73. They may be asking whether our entire description of cosmic history is too simple. Why scientists resist saying that too soon. At the same time, there is a reason researchers remain cautious. History is full of anomalies that faded. Instruments improve, calibrations tighten, errors once hidden become visible. Grand interpretations shrink back into ordinary corrections. Science learns humility from those moments. That is why the best researchers do not rush to announce the death of the standard model every time tension appears. And yet restraint has its own danger, because too much attachment to the existing picture can delay recognition when the anomaly is genuinely pointing somewhere new. This balance is difficult. Be skeptical enough to avoid fantasy. Be open enough to avoid blindness. That is the psychological burden of frontier science. And in cosmology right now, that burden is unusually heavy, because the evidence is strong enough to disturb confidence, but not yet clean enough to settle the replacement. That leaves the field in an unstable middle ground. The next wave may decide the tone of the decade. There are moments in science when the next few years matter more than the previous 20. Not because the earlier work was unimportant, but because the groundwork has finally become precise enough that the next measurements can change the emotional climate of the field. This may be one of those moments. If upcoming observations continue to reinforce the Hubble tension while also sharpening related questions about dark energy and large-scale structure, then cosmology may enter the 2030s with a serious case for revising its standard framework. But if new measurements begin to close the gap, identify overlooked systematics, or reveal that several methods were never as independent as they seemed, then the current crisis may come to be remembered as a painful but ordinary phase of refinement. Right now, both futures remain possible. That is what makes the present so tense. We are no longer at the beginning of the mystery. We are near the point where the mystery starts choosing its form. Why this matters beyond cosmology. It is easy to imagine this as a specialist dispute, something that only matters to astronomers staring at equations and redshift plots. But the stakes are broader than that. Cosmology is the closest thing humanity has to a full-scale history of existence. It tells us how the universe began to take shape, how matter organized itself, how the first structures emerged, how expansion changed over time, and what the long-term future of everything may be. So when a problem appears at the center of that story, it matters in a way that goes beyond one field. It affects how confidently we speak about the age of the cosmos, the architecture of reality, and the forces governing the largest scales imaginable. That does not mean all those things are suddenly unknown. It means the framework connecting them may be less final than we once hoped. And that, in science, is one of the most exciting and unsettling realizations possible. A universe that may be more dynamic than we thought. There is a deeper emotional thread running through all of this. For a while, modern cosmology seemed to be converging on a picture that was strange but stable. The universe was made mostly of dark ingredients we did not fundamentally understand, yes, but those ingredients at least behaved in consistent ways. Dark matter pulled, Dark energy pushed, space expanded, the equations held. Now that confidence feels less automatic, maybe the dark energy term is not truly static. Maybe the bridge from the early universe to today is not as smooth as the model assumes. Maybe the cosmos has been more dynamic, more layered, and more historically complicated than the cleanest version of lambda CDM suggests. If so, then the future of cosmology will not be about polishing an already finished map. It will be about discovering that the map had blank regions hidden beneath its neat lines. That is a very different kind of scientific era, and many researchers can feel it approaching. The universe does not owe us simplicity. This may be the most important lesson in the entire story. We often want the universe to be elegant in ways that match our mathematical instincts. We want the best model to be simple, coherent, and complete. We want the last few tensions to be technical details on the edge of an otherwise settled picture. Sometimes nature allows that. Sometimes it does not. The universe does not owe us a clean ending. It does not owe us one missing particle, one corrected calibration, one beautiful fix that makes every tension disappear. It may turn out to be stranger than the framework we built to describe it. And if that is true, then the Hubble tension will be remembered not as an annoying disagreement, but as one of the first clear signs that precision cosmology had finally reached the edge of its old confidence. That would make this more than a dispute over expansion. It would make it a turning point. The story is now moving toward judgment. Theories have spoken, measurements have multiplied, assumptions have been tested, excuses have grown thinner. Now the field is waiting for the next rounds of evidence to do what speculation cannot, to decide whether this is the beginning of revision, or the last difficult stage before reconciliation. And that is where the story becomes most gripping. Because we are not watching a solved universe. We are watching a universe under cross-examination. A universe that appears to tell one story through its oldest light, another through its nearby structure, and possibly a third through the behavior of dark energy. There is a moment in every scientific age when a question stops being technical. It stops belonging only to specialists. It stops sounding like a disagreement over method. It stops living inside graphs, equations, and conference talks, and instead it becomes something larger, a test of whether our picture of reality is actually finished. That is where this story may be heading. Because if the Hubble tension is not a calibration problem, not a statistical accident, and not a misunderstanding that vanishes with cleaner data, then the consequences are far bigger than one disputed number. They reach into the structure of modern cosmology itself, not in a theatrical sense, not in the sense that everything we know is wrong, but in the far more serious sense that one of our most successful models may no longer be complete enough to describe the universe at the precision we have now reached. And when that happens in science, the next phase is never simple. A model does not collapse all at once. It begins to lose its monopoly on confidence. That is how paradigm shifts usually begin. What a real scientific shift actually looks like. People often imagine scientific revolutions as dramatic moments. One discovery, one paper, one brilliant mind stepping forward with the final answer. Reality is almost never that clean. A real scientific shift usually begins with a model that still works very well, but not perfectly enough anymore. At first, researchers try to save it, then they modify it, then they test alternatives, then they keep the old framework because nothing better yet explains more. And for a while, the entire field lives in an uneasy in-between state. That is the stage cosmology may be approaching now. Lambda CDM still explains a tremendous amount. No serious scientist can simply throw it away. But the confidence surrounding it is no longer as effortless as it once was. That change matters. Because science does not move forward only when new answers appear. It also moves forward when old certainty weakens. Once that happens, the intellectual landscape changes. Ideas that once seemed unnecessary become worth testing. Questions that once sounded speculative become respectable. Measurements that once looked like refinements become decisive. That is how a field prepares for transformation before transformation officially arrives. The difference between wrong and incomplete. This is one of the most important distinctions in the whole story. If the standard model of cosmology is in trouble, that does not mean it was useless. It does not mean it failed. And it does not mean scientists were deluding themselves. It may simply mean the model is incomplete. That is a very different thing. An incomplete model can still be brilliantly successful. It can still predict vast ranges of reality. It can still serve as the best framework available for decades. Newtonian gravity was not useless because Einstein went deeper. It remained extraordinarily effective within its domain. The same could happen here. Lambda CDM may survive as an approximation, a limiting case, or the visible portion of a larger framework that includes behavior we have not fully mapped yet. That possibility is not a defeat for science. It is how science works at its best. We build the strongest map we can, then precision improves, then the map reveals its missing regions. That is not collapse, that is progress under pressure. Where the missing chapter could be hiding. If the model really is incomplete, then the missing piece must live somewhere specific. That is what makes the current moment so intense. The disagreement is not infinite, it is structured. The early universe tells one story, the late universe tells another. The bridge between them looks increasingly suspicious. So where could the hidden chapter be? It could be in the early universe itself. Perhaps there was an ingredient present briefly that changed the cosmic timeline before fading away. It could be in dark energy. Perhaps the force driving cosmic acceleration is not constant, but evolving. It could be in gravity. Perhaps the rules governing expansion and structure on the largest scales are not exactly what we assumed. Or it could be something more subtle, a deeper interaction between ingredients we currently treat as separate. That is what makes the problem feel so alive. The missing piece is not some abstract possibility floating everywhere. It must leave traces. It must affect the expansion history. It must reconcile the pattern of evidence. And sooner or later, if it is real, it must show itself consistently across multiple observations. That is why the current phase matters so much. Cosmology is no longer just speculating about hidden possibilities. It is trying to corner them, what scientists fear most. There is a possibility that quietly haunts every field facing a tension like this. Not that the model is wrong, not that the anomaly is false, but that the truth is messier than either side wants, because neat solutions are emotionally satisfying, One instrument was biased, one parameter was misestimated, one new field solves it all. One elegant theory replaces the old one. Those are the endings people dream about, but the universe may not offer one. It may turn out that the Hubble tension reflects a convergence of effects, small observational limitations, subtle model incompleteness, and new physics that does not arrive in one dramatic package. That kind of answer would be harder to celebrate, but no less important. In fact, it might be more realistic. The history of science is full of moments when reality did not reveal itself in one clean gesture. Instead, truth emerged through overlapping corrections that only looked obvious in hindsight. That may be where cosmology is heading, not toward one thunderclap, but toward a slow, undeniable rearrangement of what counts as complete. If dark energy moves, everything moves with it. Among all the possible missing chapters, dark energy remains one of the most dangerous. Because dark energy is not a decorative piece of the model, it dominates the large-scale future of the universe. If it changes over time, then the whole story changes with it. The pace of expansion changes. The interpretation of observational history changes. The long-range fate of the cosmos changes. The relationship between the early universe and the present changes. That is why hints of evolving dark energy create such unease. They threaten not just one number, but the stability of the timeline itself. For years, cosmologists could treat dark energy as mysterious but simple. Now there is a growing possibility that it may be mysterious and dynamic. That is a different universe. Not a universe where everything we know disappears, but one where the deepest driver of cosmic expansion may have a history of its own. And once a component as powerful as that becomes historical rather than fixed, cosmology becomes less like solving a static equation and more like reconstructing a long, changing drama. Why this would be a historic moment? If this tension really leads to a revision of the standard model, then we may be living through one of the rare scientific moments when humanity catches reality in the act of refusing our best summary. That does not happen often. Most of the time, scientific progress is incremental. It sharpens, organizes, and extends what we already know. But sometimes the sharpening itself creates the rupture. The measurements become so good that the old confidence can no longer survive unchanged. That is a historic kind of transition, not because it is loud, not because the public notices immediately, but because it marks the point where knowledge stops being a finished structure and becomes a live reconstruction again. That may be what is happening in cosmology now. For a while, the field looked as though it was moving toward a stable precision framework. A strange framework, yes, filled with dark matter and dark energy, but stable enough to serve as the backbone of the cosmic story. Now that stability is being questioned, and when the backbone of a field becomes uncertain, the whole field becomes intellectually electric. The universe as an unfinished story. One reason this problem feels so gripping is that it changes the emotional tone of cosmology. A settled model gives the universe a certain character. It feels mapped. Its mysteries remain, but its architecture feels known. An incomplete model changes that feeling completely. Suddenly, the universe is not just mysterious in its details. It is unfinished in its narrative. That is a much deeper kind of uncertainty, It means the story from the Big Bang to today may contain a transition we have not fully identified. It means the invisible forces shaping reality may have been more active or more variable than our equations assumed. It means the universe may not be a static system governed by a small set of clean constants, but a historical system whose deepest ingredients have evolved in ways we are only beginning to detect. That possibility does not make cosmology weaker. It makes it more alive, because a universe that still resists summary is a universe still capable of surprising us at the highest level. What the next decade could bring. If the current tensions hold, the next decade in cosmology may be defined by a very different kind of work, not just refining parameters, not just making prettier maps, but deciding which assumptions deserve to survive. That is a much harder task. Future surveys, improved supernova calibrations, gravitational wave standard sirens, lensing measurements, galaxy clustering data, and deeper studies of cosmic expansion history will all contribute to the same question. Is lambda CDM the final clean summary of the observable universe, or only the best temporary one? That is the real trial underway, and the answer matters enormously, because if the model survives, it survives stronger than before. If it fails, then the replacement will not be a small footnote. It will redefine how we describe the largest known structure of reality. Either outcome is significant, but only one of them turns this moment into a turning point for physics itself. A field standing on the edge of self-correction. There is something almost beautiful about this stage of science. A successful field grows confident, its equations work, its predictions hold, its framework begins to feel like solid ground. Then precision improves further, and the solid ground starts to tremble, not because the science was weak, because it was strong enough to expose its own limits. That is what self-correction looks like at the highest level. Cosmology may now be standing exactly there, at the edge where success stops being comforting and starts becoming revealing. That is not failure. That is one of the noblest things science can do. To build a model strong enough that reality itself can later show where the model runs out. We may be closer than we think. From the outside, the Hubble tension can sound like a niche argument between experts. But inside it lies something much bigger, a possible sign that the universe is more dynamic than our cleanest framework suggests, a possible sign that dark energy is not as simple as we hoped, a possible sign that the bridge between the beginning of cosmic history and the present still contains hidden architecture. And the remarkable thing is this: we may be close enough now to actually find out, not through philosophy, not through guessing, but through observation powerful enough to force the issue. That is why this moment matters, because humanity rarely gets to watch one of its deepest models stand before evidence strong enough to change the story. And when that happens, we are not just learning new data. We are watching the boundary between the known universe and the deeper universe begin to move. The story is now bigger than the tension. By now, the Hubble tension is no longer just a disagreement over expansion. It has become a stress test for the entire logic of modern cosmology. A question about whether the universe is governed by the stable, elegant summary we built, or by something slightly stranger, slightly more dynamic, and slightly less finished than that summary allows. That is why this story matters so much, because whatever happens next, the field will not return unchanged. If the tension fades, cosmology will have learned how fragile precision can be. If the tension deepens, cosmology will have learned that one of its proudest frameworks was only part of the truth. Either way, the universe has already... There is a strange psychological effect that happens when science appears to settle a great question. The universe does not become smaller, it does not become less beautiful, but it becomes calmer. Its mysteries still exist, yet they begin to feel framed, contained, placed inside a structure we trust. That is what modern cosmology had slowly been building. For decades, the picture was growing sharper. The universe began with a hot, dense origin. Space expanded, matter condensed, the first stars ignited, galaxies assembled, dark matter shaped structure, dark energy accelerated expansion. And across billions of years, the largest known story of existence could be told with surprising coherence. It was a breathtaking achievement, not because every question had been answered, but because the unanswered questions seem to live inside a stable map. That is why the Hubble tension feels so unsettling. It does not merely challenge one number, it changes the emotional texture of the map itself. Because once a contradiction appears near the center of the cosmic story, the universe stops feeling fully framed. It begins to feel open again. The difference between mystery and instability. Human beings can live quite comfortably with mystery. In some ways, we even like it. Mystery leaves room for wonder. It gives science a future. It reminds us that reality is larger than our current tools, but instability is different. Mystery means there are blank spaces on the map. Instability means the map itself may need revision. That is a much more powerful feeling. It means the story we thought we understood may still be provisional in ways we did not fully appreciate. It means the framework connecting the oldest light in the universe to the galaxies around us now may not be as secure as we hoped. It means our grand explanation may still be, in some sense, a draft. That word matters. Because drafts are not failures, they are working versions, useful, impressive, often brilliant, but not final. And perhaps that is what this moment in cosmology is forcing us to confront, not that we know nothing, but that even our deepest explanations may still be unfinished manuscripts. Why that matters to people beyond science. It would be easy to say, this is only important to physicists. After all, most people do not spend their lives thinking about the Hubble constant, baryon acoustic oscillations, or whether dark energy evolves with time. But that would miss the deeper point. Cosmology is not just another technical field. It is humanity's attempt to answer the largest possible background question: what kind of universe are we living in? Not metaphorically. Literally, how old is it? How did it grow? What is it made of? What forces shaped it? What future is it moving toward? These are not minor academic curiosities. They are the widest frame in which all human life exists. So when that frame begins to wobble, it affects something deeper than specialized knowledge. It changes the relationship between human certainty and cosmic reality. It reminds us that even at the height of our instruments, our equations, and our computational power, the universe can still reserve the right to surprise us. And there is something humbling about that. The arrogance of finished stories. Every civilization has been tempted by finished stories, stories that explain where we are, stories that organize the heavens, stories that transform confusion into order. This is not a weakness unique to science. It is part of human thought itself. We want coherence. We want structure. We want the world to make enough sense that our place inside it feels legible. Science is the greatest method ever built for testing those stories against reality. But science is still practiced by human beings, and human beings are always vulnerable to a subtle form of arrogance. The belief that because a model works beautifully, reality must now be essentially settled. The Hubble tension pushes against that arrogance. It does not destroy science, it vindicates it. Because the whole reason this contradiction matters is that scientists did not stop measuring once they had a successful model. They kept looking, they kept refining, they kept testing, and eventually the universe responded with resistance. That is not a failure of science. That is science doing exactly what it is supposed to do, building explanations strong enough that reality can expose their limits. When precision creates humility, there is an irony hidden inside all of this. The Hubble tension exists because cosmology became extraordinarily precise. If the field were vague, the contradiction could hide. If the instruments were weak, the disagreement could blur away. If the theory were loose, nobody would notice the crack. But the crack became visible precisely because the science became powerful enough to see it. That means this is not a story about ignorance. It is a story about the kind of knowledge that becomes so sharp it starts discovering the boundaries of its own assumptions. That is one of the highest forms of humility science can produce, not the humility of knowing nothing. The humility of knowing a great deal and still being forced to admit that the deepest layer may not yet be complete. That kind of humility is rare. And in a world that often mistakes confidence for truth, it may be one of the most valuable intellectual virtues we have. The emotional shock of an unfinished universe. For a while, the modern universe felt strange but settled. Yes, most of it was invisible. Yes, dark matter and dark energy were deeply mysterious, but the broad structure seemed to hold. There was comfort in that. The equations worked. The timeline fit. The largest scales of reality appeared to be describable by one elegant, if incomplete, framework. Now that comfort is weaker, and what replaces it is not chaos. It is something more interesting. A universe that feels active again. A universe that feels less like a solved diagram and more like an unfolding investigation. That changes the emotional tone of cosmology entirely. Instead of standing at the end of a great explanatory journey, we may still be somewhere in the middle of it. That realization can be unsettling, but it can also be exhilarating. Because an unfinished universe is a universe still capable of revealing major truths within living memory. Why the Hubble tension feels larger than itself. Some scientific anomalies remain local. They matter within one field, maybe one subfield, and rarely escape those boundaries. This one is different because the Hubble tension touches the timeline of the universe. It touches the meaning of expansion. It touches the behavior of dark energy. It touches the reliability of our cosmic bridge between beginning and present. That gives it a kind of symbolic power. It becomes more than a disagreement over techniques. It becomes a sign that our grandest explanation may still contain missing architecture. And missing architecture matters. A crack in a wall is one thing, a crack in a foundation is another. No one yet knows whether this problem will become that serious, but the fact that it might is enough to change how the story feels. Because once a foundation becomes questionable, every flaw built on top of it is seen differently. The human scale inside the cosmic scale. There is something else buried inside this problem that is easy to miss. Cosmology deals in absurdly large things, galaxies, billions of years, vast structures, the expansion of spacetime itself. It can feel so distant from everyday life that people assume it has no human scale at all. But that is not true. Its human scale lies in what it says about our relationship to truth. We are a small species on a small planet, orbiting an ordinary star, inside one galaxy among hundreds of billions. And yet somehow we built instruments capable of reading the afterglow of the early universe, mapping the distribution of galaxies across cosmic time, and noticing when the expansion history of reality does not quite line up. That is astonishing. What makes it even more astonishing is that we can reach this height of understanding and still be wrong in important ways. There is something deeply human in that combination: brilliance and incompleteness, reach and limitation, confidence and correction. The Hubble tension is in part a story about the cosmos, but it is also a story about us, about what kind of creatures we are, creatures capable of grasping almost unimaginable scales, yet still humble enough at our best to let the evidence overturn our favorite summaries. If our grand explanations are drafts, that changes everything. A draft is different from a myth. A myth can be false from the beginning. A draft can be profoundly true and still unfinished. That may be the best way to think about the current moment. The modern cosmological model may be one of the greatest drafts humanity has ever produced. It may describe the broad arc of the universe with remarkable accuracy. It may capture the right structure in most respects. It may survive for decades more as the backbone of cosmic explanation, and yet it may still be missing something essential. That does not weaken its achievement, it deepens it. Because the closer a draft comes to reality, the more meaningful its remaining errors become. Small errors in shallow theories do not matter much. Persistent errors in powerful theories matter enormously. They point toward the next layer. That is why the Hubble tension has so much weight, not because it proves everything is wrong, but because it may be pointing toward the next layer of the cosmic story. The universe may be telling us to widen the story. There is always a temptation, when faced with an anomaly, to force reality back into the old frame, to smooth the contradiction, to prefer the explanation that preserves comfort, to assume the map is right and the data are merely misbehaving. Sometimes that instinct is correct. Sometimes the anomaly does disappear. But sometimes the anomaly is reality's way of saying the frame itself is too narrow. That may be what is happening here. Maybe the universe is not refusing explanation. Maybe it is refusing an explanation that has become too rigid. Maybe the cosmic story we built is broadly true, but too compressed, too clean, too static, too eager to describe a changing universe with a framework that behaves as though the deepest ingredients remain fixed and simple. If that is true, then the next stage of cosmology will not just be about repairing a disagreement. It will be about widening the story. Why this is one of the most exciting moments in science. Most people never get to live through a period when one of humanity's grandest explanatory systems may be shifting under the pressure of new evidence. Usually the foundations are either too old to witness changing or too incomplete to feel foundational at all. But here, something unusual is happening. We have a mature framework. We have precision tools. We have deep data. We have a real tension, and we may be close enough to the truth for the next stage to become visible. That is an extraordinary place to be, because it means we are not just inheriting science. We are watching it revise itself at the highest level. That is one of the rare moments when knowledge becomes dramatic without losing rigor. Not drama in the cheap sense, drama in the deepest sense. The visible moment when reality refuses to stay inside the boundaries of our strongest draft. We are not standing at the end. Perhaps that is the real meaning of this whole crisis. Not that the universe is broken. Not that science failed. Not that certainty was foolish. But that we are not standing at the end of the story. We only thought we were closer to the end than we actually were. That difference matters because an ending feels closed. A middle feels alive. And if cosmology is still in the middle, still revising the relationship between the early universe, the present universe, dark energy, expansion, and structure, then we are living in a time when one of humanity's greatest narratives remains unfinished in real time. That is not bad news. It is one of the most intellectually thrilling facts imaginable, the last comfort we may have to lose. There is one final comfort that unresolved cosmology may take away. The comfort of thinking that the largest truths have already been framed and that everything left is detail. Maybe that is not true. Maybe the largest truths are still being negotiated. Maybe even now, with all our technology and all our equations, the universe is still withholding something fundamental. Maybe the final shape of cosmic history is not yet. Most people imagine that when science changes, it changes loudly. A headline, a breakthrough, a single experiment, a dramatic announcement that the old picture has fallen and a new one has arrived. But reality is often much quieter than that. Sometimes the deepest shifts begin in silence, not with a collapse, but with a mismatch, a number that refuses to settle, a model that still works but not cleanly enough anymore. A set of measurements that continue to sharpen, while the disagreement inside them refuses to disappear. That is what makes this story so eerie, because the universe did not confront us with an obvious impossibility. It confronted us with a contradiction patient enough to survive year after year, a contradiction subtle enough to be doubted, but persistent enough to become dangerous. And maybe that is how reality changes our minds most effectively. Not by shouting, by refusing to stop disagreeing. The quiet danger of a persistent anomaly. A one-time anomaly is easy to dismiss. Science is full of them. An instrument drifts. A sample is biased. A calculation gets corrected. A strange result appears, attracts excitement, and then fades into footnotes. But a persistent anomaly is different. It begins to accumulate weight, not all at once, not dramatically, just enough year after year that the burden slowly shifts. At first, the burden is on the anomaly. Prove that you are real. Prove that you are not noise. Prove that you are not an artifact of method. But if the anomaly survives, the burden moves. Eventually, it no longer has to prove itself. The model has to explain why it keeps surviving. That is where the Hubble tension has become so unsettling. Because for years, the contradiction remained small enough to doubt and serious enough to matter. It lived in that uncomfortable zone where no honest scientist could ignore it, but no careful scientist could claim final meaning too soon. That middle zone lasted a long time, and maybe that is the clearest sign that this is not a normal problem. Normal problems get cleaned up. Normal mistakes reveal themselves. Normal tensions shrink when the tools improve. This one stayed. The universe has been contradicting us politely. That may be the strangest part of all. The universe has not humiliated our model. It has not shattered it in public. It has not made the standard picture obviously ridiculous. Instead, it has done something far more unsettling. It has contradicted us politely. The cosmic microwave background still works beautifully. Large-scale structure still makes sense in astonishing detail. Dark matter still explains patterns that would otherwise be deeply confusing. Lambda CDM still holds together across huge stretches of observation. And yet there is this fracture, not large enough to erase the model, not small enough to ignore, just there, like a line in glass, visible only because the glass is so clear. That is what makes the situation so psychologically difficult. If the universe had destroyed the model outright, the next step would be obvious. If the universe had confirmed the model perfectly, the next step would also be obvious. But instead, it left us in the narrow corridor between triumph and revision. That corridor is where science becomes most tense, why the final judgment may not look dramatic. There is a temptation to wait for a decisive cinematic moment. The paper that changes everything, the survey that settles the debate overnight, the final graph that forces universal agreement. That could happen, but more often scientific judgment arrives another way, through accumulation. One new result does not end the argument, then another narrows the options, then another makes one explanation harder to defend, then another confirms a pattern that was once deniable. Eventually, the field crosses a threshold, not because one result was magical, but because disbelief became harder to maintain than revision. That may be how this story ends, not with a bang, with a narrowing of plausible systematics, a narrowing of viable theories, a narrowing of the space in which the standard model can remain untouched. And once that narrowing becomes too severe, the conclusion may not feel sudden at all. It may feel inevitable. That is often how the deepest scientific changes happen. They look controversial right up until the moment they start looking unavoidable. The emotional weight of inevitability. Inevitability is a strange thing in science. It does not feel like excitement at first. It feels like resistance wearing out. People defend the old interpretation, then they qualify it, then they preserve what they can. Then, almost without anyone declaring a formal surrender, the language changes. What once sounded radical begins to sound reasonable. What once sounded secure begins to sound provisional. What once sounded like a nuisance begins to sound like a clue. That is how a field slowly realizes it has crossed into a new era, not by celebrating the loss of certainty, but by adapting to it. Cosmology may be moving through exactly that kind of transition, not all at once, not unanimously, but perceptibly. The words are changing, the caution remains, but the confidence is softer. The standard model is still central, but less untouchable. The anomaly is still debated, but less dismissible. These are not final answers. They are signs of a field that feels reality pressing back. What it means if reality has been right all along. There is another way to think about this crisis. What if the universe is not becoming strange now? What if it was always this way? And only now have our tools become sharp enough to notice? That changes the emotional meaning of the whole story. It means reality did not suddenly change. Our access to it changed. The contradiction was always there. The missing chapter was always there. The possible dynamism in dark energy, the incompleteness in the bridge from early to late time, the subtle limits of our standard model, all of it may have been written into the cosmos from the beginning. We just were not yet precise enough to catch it. That is one of the most humbling possibilities in all of science, because it means the universe can tolerate our confidence for a long time. It can allow a theory to succeed brilliantly. It can even allow that theory to become the dominant story of reality. And still, underneath that success, it can preserve a deeper truth that waits patiently for better measurements to reveal it. That is not the universe betraying us. That is the universe being exactly what it has always been, larger than our summaries, the long patience of the cosmos. Human beings are impatient creatures. We want the answer while the question is still new. We want the solution while the anomaly is still surprising. We want resolution on a timescale that feels emotionally satisfying. The cosmos does not care about that. It has had nearly 14 billion years to become what it is. It can afford patience, and maybe that is what makes this entire problem feel almost haunting. The universe did not rush to reveal its contradiction. It let us build our best framework first. It let us grow proud of its elegance. It let us describe the cosmic story with enough coherence that we began to feel we had reached stable ground. Only then did the deeper discomfort become visible, not because the universe changed its mind, because we got close enough to hear the hesitation in its answer. A crisis measured in precision, not chaos. There is something important about the way this contradiction arrived. It did not come through spectacle, it came through precision. That matters. Because a crisis born from precision carries a special kind of authority. It means the problem is not emerging from confusion alone. It is emerging from the sharpening of the very methods that made the model powerful in the first place. The better we measured, the more carefully we cross-checked, the more rigorously we compared the early universe to the late one, the more the contradiction refused to leave. That does not guarantee a revolution, but it gives the anomaly dignity. It makes it harder to wave away as the symptom of a sloppy science. It shows that the field is confronting the problem from a position of strength. And that may be why this story feels so compelling even to people outside physics. Because it is not about ignorance colliding with mystery. It is about mastery colliding with its own limit. When the evidence becomes impossible to unsee. There is a stage in every major scientific dispute when the evidence has not yet solved the problem, but it has changed the way the problem can be looked at. Once you reach that stage, you cannot go back. You cannot pretend the anomaly was never serious. You cannot recover the old innocence of confidence. You cannot look at the model in quite the same way again. That is where cosmology may already be. Even if the Hubble tension were eventually resolved inside the standard model, the field would not emerge unchanged. The episode has already revealed how dependent cosmology is on bridges between epochs, assumptions about unseen ingredients, and interpretations that look stable until precision rises high enough to test them mercilessly. That knowledge will remain. And if the tension deepens instead of dissolving, then this current period may later be remembered as the stage when the evidence became impossible to unsee, even before the final explanation existed. That is often how history looks in retrospect. The signs were there, the resistance was understandable, the verdict arrived slowly, but once it arrived, everyone could see that reality had been signaling the problem for years. We may be living inside the turning point already. There is a habit of imagining turning points as events that happen after uncertainty ends, but often the turning point is the uncertainty, the awkward period, the unresolved years. The stage where the old framework still stands, but no longer stands unchallenged. That may be where we are now, not waiting for the turning point, living inside it. The measurements are improving, the constraints are tightening. The questions are becoming sharper. The old confidence is being tested in real time. And if that is true, then this moment has a very unusual kind of significance. We are not just watching scientists debate a technical issue. We are watching a civilization test whether one of its grandest descriptions of reality is complete. That is a rare thing. It does not happen every generation. The cosmos may be preparing a quieter kind of revelation. Perhaps the final revelation will not be dramatic at all. Perhaps there will be no singular shock, no headline clean enough to summarize the real change. Perhaps the truth will arrive the way dawn arrives, not in one instant, but by making darkness less defensible minute by minute. A new survey sharpens the pattern. A new cross-check removes another excuse. A new method leans the same direction. A new analysis tightens the timeline. A new constraint leaves less room for the old story to remain untouched. And then one day, the field looks around and realizes the revision has already happened. That would be fitting, because the Hubble tension itself never behaved like a thunderclap. It behaved like a steady pressure, a quiet contradiction, a patient refusal, a universe that kept answering differently depending on how it was asked. Why should its resolution come any other way? The final approach to the edge. By now, the story has become larger than any one telescope, any one team, or any one disputed value. It is about whether the deepest framework of modern cosmology is fully stable or only almost stable. It is about whether dark energy is truly constant, whether the timeline of expansion is fully understood, and whether reality has been revealing, slowly, carefully, almost reluctantly, that our strongest cosmic explanation is not the last one. That is what gives this whole mystery its cinematic force, not the possibility that science has failed, but the possibility that science has become precise enough to stand at the edge of. In the end, the most unsettling possibility is not that the universe is broken. It is that our explanation of it may still be unfinished. That is a very different kind of discomfort. Because an unfinished explanation does not mean we have failed. It means we have reached the limit of a framework that once felt almost complete. And maybe that is where modern cosmology stands now, not in ruins, not in confusion, but at an edge between a universe that can still be described by the model we built and a universe that may be asking for a deeper one. For years, the standard cosmological picture gave us something extraordinary, a coherent history of reality on the largest scales ever studied. It told us how the early universe cooled, how matter gathered, how light escaped, how galaxies formed, and how expansion came to dominate the architecture of everything we see. That achievement remains one of the great intellectual triumphs of our species, and yet now, at the center of that triumph, there is a fracture, a small one if you measure it carelessly, a profound one if you understand what it touches. Because the Hubble tension is not merely about whether the expansion rate is 67 or 73. It is about whether the universe tells one continuous story from its earliest light to the galaxies of the present day, or whether somewhere in that story something happened that our best model does not yet know how to say. That is why this matters so much. It is not just a technical disagreement. It is a question about whether reality has been more dynamic, more layered, and more historically complicated than our cleanest equations allowed us to believe. A cosmos that still holds something back. There is a certain kind of comfort in believing that the deepest truths are already framed, that the great map exists, that the remaining work is detail, that the largest questions have already been answered in structure, if not in every mechanism. The Hubble tension takes that comfort away, not completely, but enough to matter. It reminds us that the universe can still withhold the final piece. It can still allow a model to work brilliantly, almost majestically, and yet remain incomplete in a place that only precision can expose. That is one of the most humbling ideas in science, because it means reality does not become simpler just because our theories become elegant. It does not become final just because our measurements become powerful. And it does not owe us a conclusion at the moment we begin to feel satisfied. The universe may still be holding something back from us, not out of malice, not out of mystery for its own sake, but simply because truth is larger than every summary we build. What this moment says about science: there is a temptation, when a great model begins to show stress, to treat that stress as failure. It is not failure. It is what success looks like when it pushes far enough. The Hubble tension exists because cosmology became precise enough to discover that its own confidence might have limits. The data became good enough. The comparisons became sharp enough. The crosschecks became independent enough. And eventually, the universe stopped giving the same answer every time it was asked. That is not the collapse of science. That is science reaching the point where reality begins correcting it at the highest level. And that is one of the most beautiful things the scientific method can do: to create explanations powerful enough that nature itself can reveal where they run out. So whatever the final answer turns out to be, this moment is already significant. If the standard model survives intact, then cosmology will have passed one of the hardest tests in its history. And if it does not, then we may be watching the beginning of one of those rare transitions when humanity's map of the universe becomes larger, stranger, and closer to the truth. Either outcome is extraordinary, the human meaning of an unfinished universe. Maybe that is why this story feels bigger than physics, because at its core, it touches something deeply human. We are creatures who want coherence. We want the world to make sense. We want the great story to feel stable enough that our place inside it can be named. And yet again and again, the universe has taught us the same lesson. Every time we think we are close to the final frame, reality opens it wider. The Earth was not the center. The Sun was not the center. The Milky Way was not the whole. Ordinary matter was not most of existence. And now even the grand timeline of cosmic expansion may not be as settled as we hoped. That pattern tells us something important, not that human understanding is weak, but that it is alive. It changes because the universe forces it to change. It grows because reality keeps exceeding the boundaries of our best drafts. And perhaps that is the most honest way to see this moment. Not as a crisis of knowledge, but as knowledge caught in the act of becoming deeper, the silence before a larger answer. Right now, we do not yet know which way this story will end. Perhaps better measurements will reveal the hidden systematic that finally closes the gap. Perhaps new surveys will show that dark energy behaves more simply than feared. Perhaps the contradiction will soften and the old framework will emerge bruised but intact. Or perhaps the opposite will happen. Perhaps the tension will sharpen. Perhaps the evidence will converge. Perhaps the standard model will survive only as an approximation of a larger cosmic history that includes something new, a changing dark energy, a missing early ingredient, a subtle correction to gravity, or some deeper architecture we have not yet imagined clearly enough to name. We do not know. That uncertainty is not a weakness in the story. It is the story, because the most important scientific moments are often the ones before the answer, when the evidence has become too strong to ignore, but not yet complete enough to fully explain itself. That is where cosmology is standing now, in the silence before a larger answer, a final thought. Maybe the real significance of the Hubble tension is not that it gives us a contradiction. Maybe it is that it gives us a reminder. A reminder that even now, with all our instruments, all our data, all our equations, and all our confidence, the universe is still capable of resisting a final explanation. Still capable of saying, "You are close, but not finished." And there is something magnificent about that, because it means the cosmos is not done revealing itself. It means the deepest discoveries may still lie ahead. It means reality is still wider than the story we currently tell about it. So the next time we look into the sky, we may want to remember this. We are not just staring into distance. We are staring into a history that may still contain missing chapters, a structure that may still hide deeper laws, a universe that has allowed us to understand it brilliantly, but not completely. And maybe that is the most honest ending of all. Not that we solved the cosmos, not that we failed to solve it, but that we have reached one of those